now that we've talked about titration, acid-base reactions, reactions in general, but especially redox titration or redox reactions, oxidation reduction reactions, the transfer of electrons, we need to spend some time talking about redox titrations. A redox titration is solved in the same use the same stoichiometry way that you do acid-base titrations, but we are using reactions where electrons are being transferred instead. So the reactions themselves may look a little funky to you when we give the balanced equation. So we're going to do three. I'm going to give you the basic background of it, but then give you three examples. One that looks what I consider to be normal to you, but then two others where we realize, oh, this doesn't look quite so normal. So the first reaction we're going to do is just a simple acid-base neutralization reaction, just a simple titration, not redox. The other two examples I'm going to do are redox titration, so you can see they're not that much more complex than a regular acid-base titration. So for solving redox titrations, we solve the solution stoichiometry problems exactly the same way you solve acid-base titrations. Solve for the moles of unknown, convert the unit to the unknown that you're trying to solve for the moles of known, convert to the moles of unknown you're trying to find. You'll often be given the balanced equation, and if it is a redox titration, I will give you the balanced equation right now, okay? You learn how to actually balance these in second semester Gen Chem. First, let's just review and do a simple, relatively speaking, simple acid-base titration. How many mils of 0.35 molar sodium hydroxide are required to completely neutralize 20 mils of 0.105 molar oxalic acid? Write down what we've got in the question. We know we have 0.350 molar NaOH, and we want to know the number of mils here. We know we have 0.105 molar oxalic acid. If you don't know what oxalic acid is, well, one, you have a balanced equation, but two, you know ic acid came from an ending of 8, oxalate. You should know your polyatomics, C2H4, C2O4, 2 minus, gosh, I'm having a hard time today, I apologize. 2 protons to make that neutral, H2C2O4. We know that it's 0.15 molar. We know we have 20 mils of it. And this gave us the balanced equation, which was nice. We didn't have to balance it. This is, again, not a redox reaction. This is just an acid-base reaction. I want to know the number of mils of NaOH to completely neutralize this. That means at the molar equivalency, when the number of moles of acid are chemically equivalent to the number of moles of base. 2 moles of base for every 1 mole of acid based on the balanced reaction. I have 0.105 moles H2C2O4 to 1 liter of H2C2O4. I have 20 mils of it, 0.02000 liters. H2O4 solution. Now, right now, if I stopped, I would have moles of H2C2O4. Now I can go ahead and use my balanced equation to convert to moles of base. 2 moles NaOH for every 1 mole H2C2O4. I've got my moles of hydroxide. I need milliliters, but I do have a concentration. And remember what that concentration means. That means 0.350 moles of NaOH to 1 liter of NaOH solution. Or I can write that as 1 liter of NaOH solution to 0.350 moles of NaOH. I want to cancel out my moles of NaOH, so I'm going to use this as my conversion. That would get me liters, and then just multiply. We know there's 1,000 mils in every 1 liter. We get 12.0 mils of NaOH as our final answer. So it would take 12 mils of a 0.350 molar NaOH solution to completely neutralize 20 mils of a 0.105 molar oxalic acid solution. Let's look at a couple examples of redox titration. An iron tablet weighing 0.960 grams was dissolved in dilute sulfuric acid. The sample was titrated and 28.5 mils of 0.0175 molar KMNO4 was required to reach the endpoint. What is the percentage by mass of iron in the tablet? So what does this all mean? It means we have some kind of tablet. Okay? This tablet weighed 0.960 grams. In the tablet is some iron and some other things. What else in there? I don't know, but some other things are in there. I put this tablet, or just let's call it iron for right now. I put this tablet in solution with some H2SO4. And then I added KMNO4 to reach the endpoint. And please fix this. I did not realize this was spelled. This should be K, capital M, lowercase n, O4. Please fix that. I'll try to remember to fix that in the notes. And I want to know percent by mass of iron in the tablet. So I want to know percent iron would be how many grams of iron over 0.960 gram tablet times 100%. I need to find the grams of iron. To do this, I need the balanced equation. Now the equation I'm going to give you is going to look a little different. It's not going to be the complete, it's not going to be the molecular equation, it's going to be your net ionic equation. The equation I'm going to give you is MnO4 minus some permanganate reacts with 8 moles of H plus 5 moles of iron 2 plus giving me Mn2 plus, Fe3 plus, 5 moles of Fe3 plus, and 4 moles of water. Students get very weirded out when they read this, and they're like, this doesn't make any sense to me. Let me clean this up to get space here. That is a lowercase n in there. This is your net ionic. This is from your KMNO4. This is from your H2SO4. Okay? Don't let it freak you out because it looks different. All this means is that my K plus is a spectator. My SO4 2 minus is a spectator. I don't care what they're doing because they're not affecting the chemistry that's happening. If I look at this, I see the iron is going from +2 to +3. It has lost an electron. It's being oxidized. If I look at the oxygen, it's -2 on both sides, hydrogen is +1 on both sides, but the manganese here is +7 to +2. The manganese is reduced. It gained electrons. That's what makes this a redox titration. But students get really weirded out because they don't see the KMNO4. They don't see the sulfuric acid. They say, I can't solve it. You can solve it, I promise. It just looks a little different. We're just giving you the net ionic. We're told we have 0.0175 molar KMNO4, and it took 28.5 mils to reach the endpoint. I'm trying to find out how many grams of iron there are in the sample. So number of grams of iron, starting with what I know, 0.0175 molar KMNO4 or MnO4 minus. Same difference because KMNO4 is a 1-to-1 ratio. So for every 1 mole KMNO4, there's 1 mole of MnO4 minus. per 1 liter of MnO4 minus solution. And I use 28.5 mils of that, 0.02850 liters of MnO4 minus. Balanced equation tells me 5 moles of Fe2 plus react with 1 mole of MnO4 minus. How did I know I was using this iron and not this iron? First 5-5, it didn't matter which one I picked, truthfully. Mathematically, give me the right answer. But it is the reactant because I am titrating. And when you're titrating, you only care about reactants. You don't care so much about the products. Now, I could say how much product was made based on this titration, but right now, the way this is asking, what I'm asking for is comparing reactants. I care about your reactants. I've got moles of iron 2 plus. I'm going to convert this to grams of iron. I don't care if you put this stuff in, but you could always say 1 mole of iron to 1 mole of iron 2 plus. Iron weighs 55.85 grams. And I get out 0.139 grams of iron. I apologize, it's just really hard to read over there. Now I can plug that in and find my actual percentages. Percent iron, 0.139 grams of iron in the sample, 0.960 gram tablet, times 100% gives me 14.5% iron in the sample. Let's do one more. The purity of a sample of sodium oxalate Na2C2O4 is determined by titrating with a standard solution of KMnO4. If a 0.5116 gram sample required 35.62 mils of 0.0400 molar KMnO4 to reach the titration's endpoint, what is the percent weight by weight sodium oxalate in the sample? You need a balanced equation. I would give you these balanced equations this semester, okay? I have 2 moles of permanganate reacting with 5 moles of oxalate and 16 moles of H plus to produce 2 moles of manganese ion, 10 moles of CO2, and 8 moles of water. It tells me in the question that I have 0.0400 molar potassium permanganate, which again 1-to-1 ratio, 35.62 mils is used up. I want to know the number of grams of sodium oxalate. Start with what I know, which is my permanganate. 0.0400 moles of MnO4 minus to 1 liter MnO4 minus solution. .03562 liters of the MnO4 minus solution. Look at the balanced equation, and it's 5 moles of oxalate for every 1 mole of permanganate. Or sorry, every 2 moles. Yes, that's definitely a 2 there. Every 2 moles of permanganate. Now that I've got moles of oxalate, I can go ahead and convert 2 moles of sodium oxalate. 1 mole of Na2C2O4 has 1 mole of C2O4 2 minus, and sodium oxalate weighs 134.0 grams. For every 1 mole. Overall, I get out here 0.477 grams of Na2C2O4. But again, I want the percent in the original sample. So the percent Na2C2O4 is equal to 0.477 grams Na2C2O4 divided by 0.5116 gram sample. Times 100% gives me 93.2%. So depending on what you're doing, 93% is pretty pure. That may work for what you need. But that, again, titrations, redox titrations work just like regular titrations, just students get really tripped up because we're using these net ionic equations. And it seems weird to see things like 16 H pluses and stuff reacting. It's very common for a redox reaction.